Alright, here we are. Let's talk about one fairly fancy statistical technique called regression. I've had a decent opportunity to use this a few times, and of all the statistical techniques out there, this is probably one that I find the most informative, even though it is, once again, based on correlation, as most of this stuff is. This is really about prediction, and once we have a bunch of observations, then we can make some predictions about stuff. So actually, I'm getting a little ahead of myself here. So regression is literally about making a prediction, right? So we're going to use it in a relationship that we've observed, and that we can then predict the performance on one variable by knowing the level of another. So if we know how much goes into something, we may be able to predict how much is going to come out. If I invest X numbers of dollars, how much is going to come out of that? Well, you can use a prediction. You can use a regression to make that prediction. You invest $500, you're probably not going to make that much money because you're not going to be able to buy enough to get into those big dollar sort of blue chip accounts and things like that. But if you invest $1 million, your rate of return is probably going to be much higher. So we could discover that using a regression, just looking at how many things, if we use that as a predictor of dollars that you invest, and then how much your rate of return is, not just raw dollars, but what's your percentage, what's your ROI, right? So if we make those, we could use the regression to analyze that and come up with that answer. Interestingly enough, regression is used all over the place, in everything from advertising to poker playing to how to find drugs that are coming into the country. The regression analysis is very popular. It's very powerful. It's very simple. And I think that's one of the things that people like about it, is that it's very powerful and it's very simple. It's easy to understand what's going on with regression, and it's not simple in the sense that it's easy to run and do the calculation and you can do it on the fly. It's simple that in the sense that you're not doing a lot of data transformations. You're just analyzing the data you have and looking for certain patterns in there. And interestingly enough, we're all very familiar with regression, and when we get there, you'll see why you're already familiar with it. It's something you all learned in 7th grade. So we're just using what you learned in 7th grade and applying it with the data and with our available data sets. All right. So let's look at the couple of criteria here. We have two things, two key words that we're going to focus on: a predictor and an outcome. So a predictor is it leads to an outcome, right? So SAT score could be a predictor. SAT score would predict, supposedly, your performance in college, right? So the predictor is the SAT score. Your performance in college is the outcome. If we do just one predictor and one outcome, or multiple outcomes for that matter, it is called a simple regression, right? One predictor, one result. You could have multiple results, but typically we're just trying to predict one thing. So, so we're going to use SAT scores to predict GPA. That's it. Okay, that's a simple regression. If we have multiple predictors, which is usually the more common scenario, to predict GPA or college GPA, we would have what's called a multiple regression. So predictors, right? So if we used high school GPA, SATs, and ACTs, we could probably be more accurate at predicting your college GPA. So using multiple predictors leads us to using something called multiple regression. Right? Other than that, there's really no difference between them. Is there one predictor, two predictors, 3, 5, 10, 12, 454? It doesn't matter. You're using either simple or multiple regression, and the core of the procedures is the same. Of course, the more predictors you use, you're probably going to account for more variance in your outcome. In other words, you'll be able to make a more accurate prediction. But you have to ask the question, which one of those predictors was the most valuable? Are all of them valuable? That type of thing. Which ones can we drop? Which ones can we not? And I'll go through some examples here in a little bit of how I've had some lucky opportunity to use this in the past. So, all right, let's look at the model itself. Using an independent variable to predict a dependent variable. So keep in mind, independent variables are now, we're talking about them as predictors. Dependent variables we're talking about as outcomes. So if we want to use this example of direct instruction, so participating in direct instruction or not, right? So then we could use that to predict their level of reading performance, say, in a year. Okay, so that's one thing that we could do. Right? The model itself, how does it look? It looks like this. The outcome, the dependent variable, equals the model, and the model, what I'm talking about here, is the regression line, right? So the regression line, we're going to see what that is here in just a minute. But so when I say the model, I'm saying the statistics that's involved in this, plus error, right? So we know we're never perfect, so we always have to include that error term. ultimately, we're going to drop the error term from this because we don't know what the error is. So it will be outcome equals the model, but we know in our heads that and we don't ever really talk about it, but we know it's there, that there's always a little bit of inaccuracy here. We can estimate what that inaccuracy is, but we really don't even talk about it that much. We just say, hey, outcome equals model, and we go from there. Ultimately, what we're going to do is we're going to take all our data points, we're going to plot them, right? So we've got hundreds or thousands of data points, and we've got, imagine SAT score along the x-axis and college GPA on the y-axis. So we're going to plot all those where those intersect. A person gets an 800 on an SAT, what's their college GPA? A person gets a 900 on an SAT, what's their college GPA? So on and so forth. We're going to keep plotting all that, and we're going to get our data. Now, we're talking about linear modeling here, all right? So trust me, there's something called curvilinear modeling, and we'll get into it here in a minute, kinda. I'm just going to mention how it's done as opposed to this, but we're not actually going to go through the formulas because it gets quite complex. Right? So what we're going to do is we're going to plot all those data points, and basically we're just going to find a line that fits it. Okay? At this point, you should start to be ringing bells back to 7th grade. You've done that before. You take all those data points, right, and you draw a line through them. You draw, oh yeah, what's it called? A best fitting line. How do you get the best fitting line? Use the method of least squares. You guys are already familiar with the method of least squares, not from 7th grade, but from a couple weeks ago. What does that sound like? Method of least squares, the sum of the square. Yep, there you go, sum of squares, right? So the method of the least squared differences from each data point to the line. So instead of a flat line now, we're going to have a line that has slope to it, and we're going to try and find that slope. Oops, kind of gave myself away here a little bit, but that's what we're going to do. So we're going to find that best fit line, the line that best represents all our data, and then we're going to do that by finding the line that is closest to each and every data point as calculated by using the method of least squares. So we're going to find that distance or residual from each data point to our line, square that difference, sum everything up, so on and so forth, and that smallest number is the line that's going to be the best fit. So as you can imagine, there's an infinite number of lines that are available here, so we have to use some relatively powerful techniques in order to come up with that line fairly quickly, which that relatively powerful technique is the method of least squares. So let's look at these best fit lines. Now here's where it's going to start to really get familiar. There's two factors in any line, if you recall what they are from algebra. Slope, in other words the gradient, and the intercept, where it crosses the y-axis. So let's move forward here a little bit because it's easier to explain in this way. So there is our regression. I'm being silent for a moment while you look at that and go, why does that seem oddly familiar? Flip things around. Drop the zeros and the ones. Drop the error term. Y equals B plus B1 x1. Right? There's Y equals B plus BX. Sound familiar? Should. Because if I restate it, you'll know right away what it is. Y equals mx plus b. It's slope. This is nothing more than just an algebraic best fit line. Okay? This is just very simple. It's that simple. Y equals b plus b1 x1. Okay? So b is our intercept, so that's the level at which we're going to cross the y-axis. So remember, y is going to be our outcome. So if we're thinking college GPA, we're going to be able to predict college GPA if we know where your college GPA would be if we didn't have any other information. That's your intercept. And we're going to add to that, okay, our b times whatever your x is. Right? So b1 is our slope. Okay? So whatever that is, and x is going to be your SAT score. So SAT score times the slope plus the intercept, and we're good. Right? Then we can know exactly where you're going to be. Okay? We do drop the error term, but as I said earlier, error is there to remind us that it's never a perfect fit. We can't really calculate it in this sense at this point, so we just kind of leave it be. Right? So like it says, time to plug and play. Once we know what the line is, once we know that the slope of the line is, then we can just plug in any value for x and come up with a value for y. So let's say we've got 1,000 kids that have participated in our study. We know where they're going to be at in terms of x's and y's. We know what their SAT scores are going to be, or we know what their SAT scores are. We captured the information about their college GPA. So now what we can actually do is take somebody and say, if our sample is accurate, right? So if it was representative, when you score a 1,050 or 1,300 on your SAT, we can reasonably predict where you're going to be at on your on your college GPA. That's the value of this, right? So we can make that type of prediction. We can also make another really fun prediction based on this, which is what happens if you go beyond the data, right? So let's say that in our sample, we had this nice increasing slope as you went up in SAT score, your GPA goes up, but we only had people that went up to, say, an 1,100 SAT. We can actually figure out and make a reasonable guess, assuming it's a linear model, we can make a reasonable guess about what would happen if you scored above, right? So that 1,100. So like I said, 1,100 was the high score. What happens if you get somebody in the future that then grabs a 1,200? Well, we could just plug in the value, say 1,200 times the slope plus the intercept, and that's where they should be at college GPA. Of course, there's a lot of things in life that are not linear like this. And there's things that are curvilinear, right? Dose response curves are curvilinear. Sometimes the best dose is not the maximum dose that you can have. Sometimes the best dose is a smaller dose, right? So you get this sort of N-shaped or U-shaped curve, depending on the type of curve it is. Well, if you think back to algebra or maybe some other type of math, once again, you'll run into that sort of phenomenon. And remember looking at parabolas and all that stuff and the lines that you used to do that, well, guess what? It was a quadratic equation, right? So if we're doing curvilinear modeling with our regression, we would use a quadratic equation rather than an algebraic one. Okay? Or it is algebraic. I lost the term there. I'm not a math guy. It's been a while since I've done all that stuff. But so a quadratic equation will give us that curvilinear estimates. And we do use that quite a bit. It's just that it's not as common and as easily understood as the basic regression is. But once you understand the core of regression, then you could go ahead and apply that curvilinear stuff in the future if you wanted to. It's easy to learn about anyway. So let's look a little more about that method of least squares. Right? Essentially what we're doing is just how accurate is the line. Residuals, this is the difference from the line to the actual data points. So we've got all our real data points out there. We're going to draw a line through it, right? So then we're going to square those differences, otherwise everything's going to add up to 0. This is the sum of squares. We're ultimately going to look for the line with the lowest sum of squares value. In other words, what's that lowest residual value that we can get when we square all these things and sum them all up? What's that lowest value? That's going to give us our best fit line, right? So that's that method of least squares. That line is our regression line. Right? So when we talk about, I have a regression line, all we're talking about is a line that was derived from the method of least squares. But we have to be able to assess how accurate that line is, right? So once we find that line, then we need to evaluate it. Okay? We're going to compare it to the mean because that's the best thing that we've got, right? Or I should say the worst thing. You'll understand why in a little bit here. Bear with me. Yeah, it's coming up. Okay. All right. So the first thing we're going to do is calculate the total sum of squares using the mean. Okay, the mean is a flat line, right? So we'll come back to that in a little bit. So the mean is a flat line, and it absolutely sucks as a predictor. So think about that SAT GPA thing. You should see, as the SATs increase, you should see the GPA going up. So in other words, you shouldn't have a flat line. But if you take all that data and average it, you will have the average college GPA for all those people, ignoring all of the SAT scores, right? So you would have a flat line. Let's say it's at 3.3. Well, so we're going to calculate that sum of squares total to get and use the mean to do that, and that's going to be our worst case scenario. If we can improve on that, then we're good. So then what we're going to do is we're going to calculate the SSR, in other words, the residual sum of squares. This is the inaccuracy of the line, right? So what's left over? What is away from the line? So we're talking about inaccuracies here, right? Then we're going to divide sum of squares model by the sum of squares total to get our squared, right? And the result here, okay, is the improvement of prediction from the mean, okay, to the model. Right? So the sum of squares model is going to give us all. We're going to have that. We've got our sum of squares. So let me try again. We've got our sum of squares total, which is the total sum of squares using the mean, and then we're going to get that. The proportion of everything that is accounted for by something other than the mean. In other words, we're going to say we're going to get that improved amount of prediction, right? So we're going to say that r squared here is the same thing that r squared was in correlation. It's variance accounted for. So we're going to say that our line is this much better than the mean. That's ultimately what we're going to get, right? And if our line is significantly better than the mean, then we say we have a significant regression. Right? If it's not better than the mean, then we have a non-significant regression line, and it's just irrelevant. Right? In other words, if it is basically if it is a flat line or close to it, or if the data is all over the show, then it's not going to be a good predictor, or it's not going to be a good model to represent our data. All right, the predictors. A mean by itself, as we talked about, does not predict any change. Right? It's a flat line. It's a bad model. So B1 equals 0. Slope equals 0. Right? So if slope equals 0, anything times 0 is 0. And then we just move on from there. So yeah, the mean is basically a bad model. Right? It's just not going to predict anything very well. So what we need to do is test whether or not our predictor is better than the mean, right? So is B1 significantly different from 0? And that's really our question. If it is, then we say, hey, our regression model is a significant model. Okay? So here's what we get. You're going to get an R value, which is a correlation, as you might remember, okay? And an R2 value, an R squared value. If that's less than 100%, so if r squared is less than 100%, and it always will be, you know there are more factors that contribute to the outcome, right? So what we know, again, that's a correlation thing, right? So if you've got two variables that correlate with each other, then you square that, and you know the variance accounted for. Well, we've got the same thing going on in a regression. When we square those things, we'll know, when we square the outcome, we'll know how much variance is accounted for in the, let's say, the college GPA by the predictor, which is the SAT score, and whatever's left over is something else contributing to GPA. Okay? We could try to model that, we could try to capture it, we could use a multiple regression to do that, and we'll talk about that in a minute. But ultimately, we always know that it's never going to be completely perfect, and there's always going to be a little bit left over, but we still want to maximize as much as possible, right? Then we're going to also get the F of the model, which is the ANOVA, right? So we're going to, regression is just a special case of ANOVA, or other way around, sorry, ANOVA is just a special case of regression. So we're always going to get that F out there, right? The likelihood that the model predicts better than chance alone. So that's the one that's comparing the B1 to 0, right? So is B1 significantly different than 0? If so, then we're saying that our model predicts better than randomness, and we have a significant model or not. All right, let's look at multiple regression. The logic is basically the same. You just have more predictors, right? So we have B0, our intercept. Now we have B1 times x1, and we have B2 times x2. Each B1, x1, B2, x2, B3, x3, B4, x4, B5, x5, all that stuff. Each one of those is your predictor. Of course, then we're going to add in error. Right? What we're trying to do is find the combination of predictors that maximally correlate with the outcome. Right? So the idea being that we're looking for, we're trying to account for all that variance. Remember, we had that r squared, which is your variance accounted for. We're trying to get that whole thing up to 100%, if at all possible, if we can. And if we can do that, then we've got quite a bit of information that we can use in the future to talk about how can we get somebody to maximize their college GPA, right? So if we take the SAT score, the high school GPA score, maybe the ACT, and maybe their attendance record, right? And we can use that to predict college GPA. Well, maybe that predicts 90% of the college GPA. Well, what's left over, that 10% that we don't know about, that we haven't captured yet, something to look for in the future to see if we can model that as well. But then we have to look at each one of those variables by themselves. So let's look at each one of those variables and move on here. So the correlation and the variance accounted for that's reported in a multiple regression is the whole model and not just a single predictor, right? So we're going to look at all those things that we had just a minute ago, the SAT, the ACT, and high school GPA, and oh, that's right, we're looking at attendance as well. So when we get our output for a multiple regression, it's just going to give us that one whole thing. It's not going to tell us each individual level yet. All right, so how much was each factor or each variable predicting? And we'll get that in a minute, but first it doesn't give you that, it just gives you the whole model. Right? So we want to know that whole picture because we want to know how well that entire package predicts that outcome, college GPA. Okay? Okay? But in order to do that, we also need to look at each one of our predictors kind of at the same time. Right? So how we get that outcome is through, there's a couple of ways we can organize those predictors. The first one is called hierarchical multiple regression. This all has to do with how it's entered into the computer, so it's kind of a little bit beyond this class, but I want you to know about it so you can know that there are ways to influence these variables, and that it's not just random how we put those things together. So in this case, we enter the predictors in a particular order. That order is based on previous research. So which one of those variables that we've talked about is going to be the best predictor? Well, we go to the research and find out. We say, okay, high school GPA doesn't predict, historically hasn't predicted as well as SATs, or SATs haven't predicted as well as ACTs, and so on and so forth. And just organize them. Say, okay, the first most important is going to be whatever, and then the next most important, and then the next most important. And it tests that accordingly. Right? So if we know that the predictor 1 is more important than predictor 2, we enter it in that particular order, right? And then it spits out the result for us, and the way the calculation is run is it looks at each and every one, and it removes the effects of one from the other, so to speak. So it removes after we look at the first one, we say, okay, that's all the variance accounted for that's available. You know, it accounted for 80% of the variance or whatever, so now you have 20% of the variance left over, so how much of that variance is accounted for by the second variable? You say, okay, that accounts for 10%, so now we're at 90 total percent, so we got 10% total left, so what's the third variable, and so on and so forth. And we keep doing it that way, and that's how it spits out the result for you. Okay. The other way to do this is called stepwise multiple regression. We've got two ways, forward and backward. So this is where we enter a list of predictors, and the computer searches for the one that best explains the model. Right? So it just does each one. It runs each one by itself. Which one best explains? Which particular predictor by itself is the best one. Right? So like it says here, say 60%. So we find one that predicts the model the best, that's 60%. Computer looks for the remaining, the next one that explains most of the 40%, and there's a special technique used here. This is called part and partialing, but again, beyond the scope of this course. But it partials out the effects of other predictors and looks for what's left over by that the one, you know, the remaining predictor on an individual level, remaining predictors on an individual level. And it repeats that until all the predictors are used up and placed in order of value. So this one produces the most, this one produces the second most, and third most. It's completely unaffected by what do you call it? By theory or anything like that. This is just letting the numbers run, right? And the computer will find you the best one, which may not match a given theory. So sometimes we want to test that. We want to use those theories to come up with the predictors in the hierarchical, so we can actually test the theory and say, yes, this was the best predictor, or no, it wasn't. So this is probably one of the most common ones that you see out there. Okay. The last method that we have here is called stepwise multiple regression, but it's backward. Right? So similar logic, except the program removes variables that do not predict the outcome. Okay? So we say that we only want variables that are significant predictors, and remember what we're doing here is it's looking at each variable and saying each variable is a significant predictor or not, and it's telling us if the whole model is a significant predictor. Right? The model contains multiple multiple predictors, but it will also allow us to look at each predictor. So in this case, what we're doing is removing variables that do not predict at a certain level. So if we're saying 0.05 is the level of significance that we're after, say, okay, does this predict at that level? And if it doesn't, then it drops it, and then it reruns the analysis and say, okay, which ones are out of all these? Let's run it again, and it continues to drop that out. Right? So it works by looking at each predictor, calculating the likelihood that it's predicting at a level higher than chance. If not, it's dropped. Then the whole calculation is redone, and it keeps doing that until it finds the 2 or 3 that are significant. So the last two methods, forward, stepwise and back, stepwise regression, forward and backward, are the most common ones. Hierarchical it's relatively common, but I think most people tend to use the forward stuff just because you're not bound by theory. It just and you can use it to confirm theory, or you can use it to disconfirm theory, and I think that's the value in it. So multiple regression, again, is very useful. You can imagine how this stuff works in advertising, and where you look at how many commercials you should buy, how much money you should invest in terms of advertising your product to get the most rates of returns and things like that. This is all over the place, and it's used in tons and tons of fields, so it's probably one of the most common statistical techniques out there, although not everyone understands it really well. They get the basic idea, but all the little details, and I've skipped over quite a few of the details, but to get into it, if you're interested, feel free to bug me a little bit, and we can talk more about how all the part and partialing works and things like that. But essentially, this is a fancy statistical technique that's based at the core on correlation, and also you are analyzing the variance in there, so it's very closely related to an ANOVA, but we talk about predictions rather than just saying there's a significant difference here. We talk about basic predictors. So you'll run into these in the literature quite a bit, so I hope you understand them a little bit more now than what you did before. Talk to you soon.